Among the 1,025 stars of the star catalog included in Ptolemy's Almagest is a star that Ptolemy describes as the last star of the river, the bright one. Given that Ptolemy's catalog contains coordinates for each of its entries, astronomers can unambiguously identify this star as what astronomers today refer to as Theta Eridani. However, this interpretation presents an immediate problem because, contrary to Ptolemy's claim, Theta Eridani is not a particularly bright star. Modern measurements put its magnitude at 2.9, far fainter than the first magnitude Ptolemy lists for it. So, did the great Ptolemy make a mistake? If he did, he certainly wasn't alone. The 10th century Persian astronomer al-Sufi also indicated that it was one of the 13 brightest stars in the entirety of the night sky. To be fair, Ptolemy also listed it as among these 13. So was al-Sufi simply repeating Ptolemy uncritically? The authors of a new paper suggest that this would have been unlikely. This is because al-Sufi is known for his work, The Book of Fixed Stars. By and large, this work is a copy of Ptolemy's star catalog with the coordinates adjusted by just under 12 3/4 degrees to account for precession. However, al-Sufi also took the time to update the brightnesses of many stars. As such, al-Sufi seems to have been double-checking Ptolemy's brightnesses, and would have been likely to notice the stark difference had there been one. Perhaps confusing the matter, the 2nd century BCE astronomer Hipparchus listed Theta Eridani as a magnitude 2.6 star, much closer to today's value. The nearness of this value to the modern one may make us tempted to accept it as true, but we must also remember that this star was the last in the river, which winds its way southward, putting the star low on Hipparchus's horizon, where passing through larger amounts of atmosphere would dim it significantly. The authors of the paper suggest that this would have dimmed the star by about 2.5 magnitudes, indicating that the star would have had a true brightness of magnitude 0, even brighter than described by Ptolemy. Taken together, it seems that several prominent astronomers across nearly a millennia all saw Theta Eridani as a bright star. In 1603, John Bayer published his Uranometria. This was one of the first works to include many stars first revealed to European astronomers thanks to the voyages south of the equator during the Age of Exploration. This extended the constellation even further south, adding several new stars, including one which would then be considered the brightest star in the constellation. If you're not aware, Bayer labeled the stars in the Uranometria roughly in order of brightness. This new brightest star he called Alpha Eridani. Thus, Theta Eridani was roughly the 8th brightest star when Bayer published his work. So how could the star, evidently brilliant for hundreds of years, fade so significantly in just a few hundred more? The authors of the paper point out that Theta Eridani isn't a single star. In fact, it's not even 2 stars, it's 3. The system is composed of a close pair of binary stars, separated, on average, by only about 0.8 astronomical units, where an astronomical unit is the distance between the Earth and the Sun. Thus, the stars orbit one another far closer than even Mercury orbits the Sun. Far removed from this, at a distance of 425 AU, over 100 times further than Pluto in our solar system, is the 3rd star, which can be resolved with a good telescope. Now, as someone with a background in astronomy, having a pair of close binary stars like this immediately brings to mind a method for substantial changes in brightness. At such distances, each of the stars feels significant gravitational forces from the other. This elongates the stars, and if one of the stars undergoes an evolutionary change that causes it to puff up, it can pass the tipping point of that gravitational balance, causing matter to spill onto the other star. This can result in matter piling up on the surface until it reaches a critical mass, resulting in a massive explosion. This is often referred to as a nova, resulting in the system being classified as a cataclysmic variable. There's just a few small problems with this explanation if applied to Theta Eridani. First, it requires that at least one of the stars be undergoing an evolutionary change causing it to expand. Most stars that we see in the night sky are in what's known as the main sequence portion of their lifetime. This means that they are converting hydrogen to helium in their cores, a very stable era, which comprises the overwhelming majority of the star's life, as this fusion process is able to produce more energy than any other type of fusion, and will correspondingly support the star against its own gravity for the longest time. Thus, we'd need to establish that one of these stars was at some critical point where its size would be undergoing some change. Second, novae of this sort are extremely short-lived. The mass piles up, explodes over a matter of days to months, blows away the incoming stream of matter, and then the system settles down again. If the mass transfer then resumes, this type of explosion can be recurrent, but it's certainly not sustained for 1,000 years. So how do the authors of this paper explain the pair appearing so bright for at least 1,000 years? First, they established that one of the stars, the larger of the two in the binary pair, is at just one of those critical evolutionary changes. Specifically, it has a spectral class of A3IV-V. To explain, the letter and the number at the beginning tells you something about the mass or temperature of the star. For historical reasons, they are ordered from most massive to least, O, B, A, F, G, K, M. Then each of these categories is broken down from 0 to 9, with 0 being the higher mass. The Roman numerals at the end correspond to the luminosity, which is also tied to the evolutionary life stage of the star. The lower the Roman numeral, the brighter the star. Stars in their stable main sequence lifetime get a Roman numeral V for 5. So putting that all together and contextualizing, the Sun is a G2V star, on the lower end of the mass spectrum, but closer to F than K, and in its main sequence lifetime. Meanwhile, the primary star in the Theta Eridani binary is an A3IV-V star, more massive than the Sun, and closer to a B-type than an F. And the Roman numeral indicates that it's not in that stable main sequence lifetime. Rather, the star has recently exhausted its supply of hydrogen in its core, moving it off of the main sequence. You'd probably expect that running out of fuel should make the star smaller and dimmer. But as hydrogen runs out and gravity squeezes the star, it can trigger fusion in the layers outside of the star's core, closer to the exterior of the star, causing the star to swell slightly. Eventually, gravity will squeeze the core of this star enough that the result of the hydrogen fusion, helium, will itself be able to undergo fusion, stabilizing the star again. But for now, the star is somewhere between these two phases, so the necessary precondition is met. For the duration problem, the authors proposed that the system did not result in a classical nova as I described. Rather, the orbit of these two stars is eccentric. They get closer and further apart throughout their orbits, making the mass spilled from one star towards the other not flow smoothly onto the second. The result would be that the process is much more complex, and would likely spill a lot of matter around both of the stars, creating a common envelope of relatively dense matter surrounding the two stars. This envelope of matter would have an increased surface area from which to radiate. But even more importantly, the authors proposed that this dense nebula around the pair could reprocess the energy from the stars, resulting in it becoming even brighter. Now, the authors don't do a very good job of explaining what this means, so I'm going to be giving my own interpretation here. But stars don't emit light just in the visible spectrum. Rather, they emit light across a large range of wavelengths. In short, the stars would also be throwing out ultraviolet light, X-rays, and gamma rays. Normally, we can't see these because we didn't evolve to see those wavelengths. However, if the envelope around the star was able to capture some of that higher energy light, it could prevent it from leaving the system, and the envelope could re-emit it at a longer wavelength, possibly in the visible portion of the spectrum, converting some of the energy that we couldn't see into light we can see, thus causing the system to brighten considerably in the visible portion of the spectrum and creating the luminosity seen by ancient astronomers. To be clear, this is still a very preliminary hypothesis, and the authors note that trying to model such a complicated process is extremely challenging. Thus, to really establish this as a viable mechanism, they suggest that astronomers study other close binary systems similar to this one, looking for those rare instances in which one of the stars is in this very short-lived phase of their lifetimes and the pair has an eccentric orbit. Unfortunately, this phase only accounts for a fraction of a percent of the star's life, so it would be extremely rare to catch one. But there are a lot of stars in the sky, which we can see with modern telescopes. And it's just possible that the ancient astronomers caught one while studying astronomy before the telescope.